So this is where we left off yesterday. So I had this picture up at the board. We wanted to get this Bordism infinity one category as a single space. So I told you yesterday what the xn's are. I told you yesterday, so for a single space, we have to define xn's, and we have to define maps between them. So I told you yesterday what the xn is. Well, I told you what the points in the space are supposed to be. So they consist of an open interval AB. So this is like here, these m's. This is open. And an m-dimensional submanifold of this open times R infinity. R infinity is just there to kind of, allow every manifold with boundary. This one-dimensional case, sorry, in this one-fold Siegel space where we only have this one coordinate, I mean, this is very easy. We actually have manifolds with boundary. Manifolds with boundary aren't that scary. So there are embedding theorems for manifolds with boundary. You can always embed them in such a way. The reason I want to stress that this is open and this is a submanifold is that I did not want to have to deal with corners, because then like smooth manifolds with corners, that starts to get annoying. I'm not saying it can't be done. It can absolutely be done. And this is a choice, a personal choice I'm making here, right? There is no one Bordism category. There are several ways we could define this, but this is a personal choice I made because I just didn't want to deal with smooth corners. And then there's this data of certain intervals, and they're marked with these little green regions here. And these intervals you should think of as places where the manifold above is nice enough that I can just cut and get a lower dimensional manifold. Okay, so there is this, the theorem, I mean, you learn this in analysis at some point in your first or second year. If you have a submersion and you take, I mean, you have a regular value and you take the pre-image, then you get a lower dimensional manifold. This is what we're using here. Okay, plus, if I wiggle around my point where I want to cut a little bit, then those will be diffeomorphic. That's like part of a Morse lemma, if you will. Okay, so again, this was a choice. I could have made different choices. I should mention here that, of course, the idea of this as a Siegel space goes back to Jacob Lurie and his beautiful expository paper on the cobordism hypothesis. And Demia Kalaka and myself, we kind of worked out the nitty-gritty details for a particular application we had in mind, namely a certain TFT. All right, so we have three conditions here. So the first one is orderedness, okay, whatever. That means that we read our Bordism from left to right. And, so the first cut, that's the first piece in the composition, that's the second one, that's the third one, and so on. And what about these two conditions? So one of the conditions, the properness, tells us that if we take, I said these are regions where we're allowed to cut. We're not cutting. I want to emphasize this. We're actually not cutting. But you should think of these as regions where we're allowed to cut if we want to. So that means that if I take some compact interval here, and take the pre-image, then the properness ensures that this will be a compact Bordism. So just a Bordism as, we would have defined before, or we know and love. And what about this third condition? As I said before, that ensures that the pre-image of a point is a manifold so that we don't get something like this where we would have to. Okay, so far so good. That's what we did yesterday. So we have these xn's here. And then I said in a Siegel space, in addition, what we need are maps between them. So I tried to use a color coding of yesterday. Well, at least on my slides, my personal notes yesterday, the colors of the board were different. But we had two kind of different types of maps. We had maps going, I'll say, to the left, and maps going to the right. And so these purple maps, the ones going to the left, they're called face maps. And these you should think of as in a category, they're like source and target. And then we have composable maps, so then we have to forget parts of things. So in the nerve of a category, if you remember, we also have these maps. So these consist of, well, we just forget some interval. We just forget some interval and we keep the Bordism. Except if I forget this interval, then I don't keep the whole bordism, but I just erase this part. Okay, so hopefully that's intuitively rather clear what's happening. The blue maps going the other way. I don't know why this keeps happening. It's not doing anything. Okay, so the blue maps going the other way, they're called degeneracy maps. And yeah. And they consist of simply doubling an interval. So I have my list of intervals. Say I0 less than I1 less than I2. And then, for instance, I just repeat one. So I wrote an equals here, but of course, if I write my list of intervals like that, I should also write this list as that. I mean, even though it's equal. But it's just doubling an interval. And you can think of it as inserting a thin bordism, something with no length in some sense. But that's just a mental image. That's not really what happens. All right, so I mean, the degenerates, it's really not that important actually for higher categories. You could also, I mean, having identities turns out to be an addition and not extra structure. So this is actually really not that important. But this is somehow the classical presentation. Again, I want to stress that this is a version of a infinity one bordism category. You might want a completely different one. It's fine. However, there should be a sense in which they're equivalent. It's equivalence of categories. So, you know, depending on your application, you might want to, you know, tweak it a little bit. All right, so the last piece is that these things are supposed to be spaces. I said it's supposed to be a simplicial space. And I'm not going to tell you what the topology is because this is, I mean, it took me a long time and a lot of headache to understand this. Probably those of you who have tried as well. But essentially, you can picture it as, you know, we're wiggling the bordism around as embedded. And also we're wiggling the intervals around. That's somehow roughly the idea. Somehow, if you wiggle around your embedded thing, then hopefully it's clear that you get a diffeomorphism between the pieces. That's actually another application of the Morse lemma, if you are curious. Okay, good. Any questions about the picture before I take it down? Yes.
So the degeneracy maps, they are just sort of bookkeeping, like they add extra bookkeeping things like of your intervals, they don't do anything to your bordism.
Absolutely, yes. And that's the way you should think of the intervals in the first place. They're a bookkeeping tool. That's all they are.
Did you already say why you want these accents to be spaces?
Not really. I just told you an infinity one category is a simplicial space, blah, blah, blah. So this goes into in the space. So I mean, so I wanted to omit those details, but there is a principle. So I just said that you should think of a path as wiggling around. And somehow you can translate that into diffeomorphism. Okay, so this is basically, it's an application of Morse lemma. If you have a family, which is a trivial bundle, and you get a diffeomorphism from the beginning to the end, something like this. And so if you remember, I said, like, you know, with this extending above thing, like we want to not end with bordisms, but we want to add diffeomorphisms above, and then isotopies of diffeomorphisms, etc. And this is a beautiful principle called the homotopy hypothesis. That's such an infinity groupoid. So we have objects, invertible guys, invertible two morphisms, etc., can be captured by a space. And like somehow to go from a space to the infinity groupoid, you take like objects are points, morphisms are paths, two morphisms are homotopies, etc. But I didn't want to kind of go into those categories. But if anybody else has questions, I'm more than happy to talk about it. And yeah, maybe this is also a good point. Maybe I should not have written space here. Maybe I should have rather written infinity group. Now, from the categorical point of view, that's actually the natural thing. It's just that we're treating a space as an infinity. Maybe conversely, like, you know, saying we want invertible one morphism, invertible two morphisms, et cetera, that's a lot of data and kind of, you know, very complicated. Conversely, maybe you should read it the other way around, say like, well, a space is just a beautiful small, you know, summary of what we mean. So maybe turn it around into, you know, definition.
Say again why this embedding into R infinity isn't necessary somehow.
It's not necessary at all. This is a choice. It's a choice that makes it easy to write down what the space is, just because then we have, you know, we can put a topology on the space of submanifolds or something. Well, some people can, let's put it that way. But it's a convenient way to get the space. And I mean, for me personally, it's also just a way of, you know, I picture bordisms. I picture them as embedded. You don't have to choose that embedding at all. And I mean, there are certainly people who would rather not include the data of an embedding. So, I mean, it's extra data, it's more info, right? It's just that we're making the space in a way that that extra info is contractible. So it's really not necessarily relevant. But certainly, I mean, you know, if you ask somebody else, maybe, you know, maybe Dan, maybe Peter Teichner and Stefan Stolz, they will say like they don't want a global embedding of the manifolds. Maybe they just want something locally at the boundary or something. These are the types of choices that I was mentioning. At this point, I'd like to take a moment and say, well, I mean, you know, this was a while ago, this bordism category, and I mean, you might want to tweak this definition, say maybe put bordisms with defects, put tangential structures, etc. So there is work in progress on making a defect category with full codimension defects as a single space. Will also has a version tailored to the relative field theories for codimension 1 defects. And Dan and Konstantin have a version in a recent paper. They also have a version of bordisms with boundaries as such a thing. Probably I'm forgetting some people, so if somebody, I'm forgetting somebody, please speak up. Yes.
I was just going to say, the obvious reason for giving an embedding is because then you don't have to think of the morphisms themselves, the categories in the space.
You mean because the space comes from the space of
Well, there are no non-identity morphisms between the tables.
Yes, that's true. Yes, yes, absolutely. Thank you. Yeah, that's a very nice remark. Yeah. Any other questions or comments?
Is this complete?
No. So yes, for like dimension 0, 1, 2, 3, maybe not even 3. And it's known not to be complete after 5. 4. There are non-trivial so-called H-cobordisms. Those are invertible cobordisms that are invertible up to homotopy, which are not mapping cylinders. So Lurie explains this very nicely in his paper. Okay, great. That was it for bordisms. All right, so of a Siegel space. And that gives us an infinity one category. So this statement actually is really true. If we want an arrow the other way, we should add a condition called completeness. And so what about going higher? So I said I want to have actually infinity k categories. So I won't do many details, but I told you somehow that this now is not much harder than this. So what happens there, I take my definition. Instead of having just one coordinate direction, I'll take k coordinate directions. Plus a Siegel condition, plus a completeness condition. And then there's a +1 condition, which ensures what's called globularity. We had some preliminary discussions about this yesterday, the difference between a double category and a bi-category, but I don't want to go into details here. So these are not so important for us right now, although they are important for defining an infinity k category. But I just really want to show you that, well, what happened from here to here is we just took a product here. So there's not that much that changes. I mean, it's like if you digested before that you have all these indices, you have all these pieces. Now, well, adding a second coordinate direction hopefully is not that much conceptually of a difference. You maybe have to start, the bookkeeping becomes harder. You have to keep track of all the directions, but conceptually, it's not that much harder. Do you agree? Do you disagree? Okay, so I'll just give a very brief indication of what now changes for boardisms. Instead of having m sitting inside an open interval times r infinity, now we put some box here, a rectangle. So this here now is a product of such intervals. And k. And then we have to replace, so we had a third condition that ensured this was a submersivity condition that ensured that preimages have the right dimension. And we have to replace that condition by a certain more general one, which again is expressed in terms of submersivity conditions. And again, I don't want to claim that, this is all super trivial and easy and whatnot, but I just want to show you that conceptually, like there's no increase in difficulty in the conceptual thing. Of course, it's a bookkeeping process, which is annoying. And you have to, make sure not to have a knot in your brain. But apart from that, like conceptually, it's not. Okay, so why do we do this? So that means we get something one might call board n minus k. And so in particular for k equals n, we will just denote this by board n. And I can't give a talk on, I can't give a mini course on higher categories in QFT without telling you about the cobordism hypothesis, so I will do that now. So reality has shown up, I don't know how many times in this week, but I want to claim that TFTs being fully local, completely local, I don't know, but fully local, is expressed in terms of this cobordism hypothesis. So TFT is now based on this category. So this gives a notion of TFT. These are called fully extended. So the first version of the statement is due to Bayes and Dolan. And the version I'll tell you today is due to Jacob Lurie. And then I hope you, yes,
For these new spaces that we're making, do we want to think of these manifolds having like little cubes or something similarly to we had little intervals before?
yes, yes, absolutely. So we have a bunch of intervals. We have intervals in each direction, but then we get grids. So if this is my rectangle, then I have little regions. Like this. So here you have an interval, and then here is your other interval in the other direction. So yes,
And you're also allowed to have not fully extending things, but then like smaller squares within that rectangle.
no, in this formalism, no. So you might have a different model for infinity n category where you can have that. But here, no. Here really, our grids really look like this. They're really kind of very well behaved. Any other questions? Okay, so since David Jordan's lectures last year were all about the cobordism hypothesis, I won't say much here also about the history and about the status of the proof, etc. But I just want you to see the statement. So I haven't told you yet about symmetric monoidal things, and I won't. But we'll start with the symmetric monoidal infinity D category. So dimensions are always D, right? So I should have put D here. So I have C as symmetric monoidal infinity D category. And then we can look at TFTs based on this bordism category. But I don't want any bordisms. I want to add some extra structure called the framing. Again, if you have more questions about this, I'm happy to comment on that afterwards, but for the talks today, it's not that relevant. And since I'm extending all the way down to points, in particular, I have a point. So I mean, if you think of the above, it's actually a little RD, but I mean, whatever. We evaluate at a point. So we get something in C. And the things that we get in C have certain properties, namely they're called dedualizable. And actually, this turns out to be a groupoid, an infinity. And the statement of the cobordism hypothesis that this is an equivalence. These fully extended named. So the power of this theorem is to say that, well, rather than write down a functor, which is a lot of work, I have to, for every such, manifold, bordism, blah, 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 give you data and then check compatibilities. Rather than doing that, I can just go into my algebraic thing, pick an object, and try to check whether these properties are satisfied. It's not like that's trivial, right? I mean, there are many papers doing this a case-by-case thing. Pick your favorite C, for certain reasons, there are certain Cs. Pick your favorite C and then try to do this. But I do claim that in certain cases, or in many cases, it's easier than the side. Okay, so for more info on that, see David's lectures. Okay, so the reason I'm First of all, I can't give a course like that and not tell you about these things, but second of all, what we will now focus on is we'll continue our walk through higher category land. So that means we need to find good options for C. And next, I will tell you about one option.
That's a good question.
Yes, sure.
So if you just have a QFT defined in the top two dimensions, always possible to find a target category that makes it fully extendable. Fully extended.
Conjecturally, yes. Proven, no. Conjecturally, yes. Maybe that's a vast conjecture. For invertible field theories, that's true. Reed and Hopkins, I mean, the thing they like to put here as the C is this universal target. So that certainly works. For non-invertible, Peter Johnson-Fried and David Reuter have a proposal for something here that is a universal thing. But universal in the sense that you can always extend down, I don't think they have. I mean, again, conjecturally, I think that could be expected, but they don't have it at present. Any other questions?
One of these is framing with other structures of the conjecture that.
Yes. So if you TFT for other tangential structures, there's a version of the cobordism hypothesis that applies if you want to replace this, say, by an orientation. So the thing is that because here you can rotate things, and well, you have an action of O of D, you can actually have an action of O of D on this side as well. And then, I mean, let's take say orientation, and you can look at the sub action of SOD, and then you're looking for SOD fixed points here. It's just doing that is freaking hard. Like, you know, for certain categories, like we even have guesses what, you know, N action could be, arguing that it is the action from the other side. You basically have to know what the TFT is that you construct to know what.
Maybe to that question, do you know also if how tangential structures may influence completeness or not? Do they? Or-
Oh, I have no idea. I don't think it does, because the H cobordisms that show up are just unoriented. They will.
I'm just.
Sorry. Yeah. Okay. No. Never mind. I take that comment back. Of course. I don't know.
Slightly confused about the answer to Ryan's question.
To Ryan's question. Yeah.
I understand the question is, can you, if you know the theory at the top two levels, is there always some way to extend down
Yes.
to a point?
Yes.
Which I would translate as, can you always find a topological boundary condition? That
Or enough topological boundary conditions.
generates everything, yes.
Yes. Yes.
How does that mesh with facts about Chern-Simons theory?
Well, so Chern-Simons theory, for instance, so Chern-Simons theory, for instance, like if you want to start and put here a particular target, say tensor categories, bimodule categories, functors, natural transformations, then it's not fully extended. But we can enlarge this category and add a missing object. You get a new category, 3 category, and now it is fully extended. That's something that Dan and Constantine and I have been talking about for a long time, and this is somehow the first, you know, that's what David and Theo basically exploit to that more general setting. Start with, say, a Merida category and then really add enough things. There's a second aspect, which I have been sweeping under the rug, is if the theory is anomalous. But then, I mean, that's a bit of a different question in some sense, because then you're starting with a different framework.
I maybe say something to Tudor's question.
Absolutely.
So when you have this possibly universal extension, like, and you want to think about C as a point as like a category of boundary conditions or something like that. In this case that you have a spiral theory, those actually won't be topological boundary conditions. In fact, there will be no dualizable objects in that category. What you really need for a boundary condition is a certain like dualizable functor from the trivial TQFT to this one. So you need to choose special objects in C of a point, and you might not have those, even though you have that category.
Thank you. So there's something more flexible here.
Yes. So this framework does not encode anomalous theories. For that, we need to do what Ryan was suggesting, have some sort of a functor from a trivial theory to something other. This is great. I mean, this is what we need, right? Translations to the other world. Anything else? Okay, so let me start with lecture 3. Algebras and Merida. So what can we possibly put here? Before we try to do fancy things like find universal targets, well, we want to have some target. So one of them was already at the board. I told you there's this bi-category called alg, where we have objects are algebras. Morphisms are bimodules. Two morphisms are homomorphisms. Again, I'm not telling you a lot of the data, a lot of stuff. I did not even tell you what composition is, so let me do that. I have something like this and something like this, then I compose by taking the relative tensor product. So this here, I will now call this alg1 of vect. And you will see why. So what about an example of a 3 category? Again, relevant in such a context. Alg1 of cat, where my objects now are braided tensor categories. Sorry, not braided, tensor categories. One step ahead of myself. Tensor categories. Morphisms are bimodule categories. Two morphisms are functors, which are bimodule functors, and 3 morphisms are natural transformations. So this is the thing I just mentioned in the conversation before about Stern-Simons theory. And well, again, I haven't told you most of what this actually is. I just gave you a very informal description of the layers. And well, is this a 3 category? And certainly it's not strict. So the question is, how do we build something like that? I kind of tried to sketch yesterday that to check that this is an actual weak 3 category would be very painful. And And certainly you can extract many things and work them out in detail, like you can find also by category sets it inside there and so on, but then there's still the question of how they really assemble to one thing. So this has appeared in various situations. So one thing I should say is to make something like this precise, we have to actually say what kind of categories. So first of all, these should be linear. But one should be much more precise than I'm going to be in this lecture series on what kind of categories. So for instance, one could take finite linear categories, and then one is in the setting of paper by Chris Douglas, and Noah Snyder, who's here. And then, I mean, one could take something like PRL, presentable linear categories, and then one is in the setting of O'Shea, Jordan, Mulligan. And it's relevant for both Tarai-Firo theory and the Witten-Reshetikhin-Tarai theory. So this is certainly something we want to have. Go up one step, there's also a 4 category. Won't write out all the layers, but now we have braided tensor cats, bimodules, and then centered bimodules. And then functors and then natural transformations. The 4 category called Alch2 of cat. Again, linear, again, same caveat as before. So this appeared in this paper here, context of the Witten-Reshetikhin-Tarai theory. There's also an Alch3. And so there's been recent thesis work by Ben Hayoun and also by Patrick Kinnear, who studied dualizability and relative dualizability in these settings. For Ben's here. Okay. Great. So if you want more information on this in relation to dualizability and what is my hypothesis again, David's lectures. But today instead, well, I'll at least try to indicate how to define something as the 2 things I just erased as Siegel spaces, higher Siegel spaces.
You feel free to reject this question. In 3 category setting
Yes.
for WRT theory.
Yes.
What's the tensor category?
What do you mean the tensor category? The one you stick in?
Sorry,
You
specific.
You stick in a modular tensor category for the WRT theory. So it won't be, I mean, that won't be 3 dualizable. You have to fiddle around with the framework a lot. Talk to Ben to make that. And I mean, we still don't have it as a full theory. We have many pieces of it, many puzzle pieces, but it's still not a complete.
Maybe a way to say it that you don't want to work in the 3 category term. You want to work in the 4 category
Okay.
and have an arrow from the trivial to real.
Yes. So here you have 4 dualizability and even invertibility. Okay, so even if you don't enjoy this kind of thing about targets of TSTs and why do I care? Billion different targets. They all seem to not completely work or something. No, not true. Not true. You might still enjoy what I'm going to tell you about now, namely factorization algebras. So Graham told us in his lectures that something a quantum field theory should have is some sort of algebras of observables. So write it. So these are a variation of an algebraic quantum field theory approach, where what you have is in your space-time, you take your open U and you assign to it some algebra, A of U. And so a QFT is a huge framework and lots of work on this. And studying quantum field theories in this way. And factorization algebras are a variation of that, namely, we make a weaker thing, in a certain sense weaker thing, and get rid of the algebra structure. But we still have some sort of multiplications around. Axiomatization, observables of a QFT, and perturbative, I should say. And the version that I will tell you about, and I mean, this goes back to ideas by Beilinson and Drinfeld and many, many others, but the version I will tell you about is due to Jacob Lurie and Costello-Guglielm. And just to give you an indication, so in this later case, so this was mostly in the topological case, mostly. And this here, they build a whole framework to do BB quantization in this framework. And of course, there's been work by many, many, many people developing this. And maybe if you're more of an algebraically minded person, you might still care. Well, I want to use it for that over there. So hopefully the things that are on that board will appear as such a thing. So for instance, we have special cases, like algebras fit in this framework, bimodules fit in this framework. EN algebras fit in this framework. In particular, rated monoidal categories fit in this framework. Or just monoidal. To algebras, we could add an A infinity, these types of things. So definition. X just has to be a topological space for us to define this thing. And I mean, it will always be a manifold later on, but like we don't need it. And then the language that is used to fully really describe what these things are oprads. If you don't know what an oprad is, I'll do a down-to-earth description in a moment. So the oprad of opens in X, we denote by open X tensor, has open sets of X as colors and an operation from some colors U to some color V if the U's are disjoint and they sit inside V. And now a pre-factorization algebra is an algebra for this opera. On X valued in some monoidal category. And so often you can think of S as being chain complexes. This is an algebra A for this operad. That is, and now comes explicit description. So if everything above doesn't make sense, this is the explicit description. So for every disjoint union of opens in V, we have a map going from tensor product of A of U1 to A of UN into A of V. I should really give this a name, but I'm not going to write it out every time. And this assignment is coherent. What that means is that if I can include opens big open, and then I have intermediate opens. Maybe I have little opens sitting inside here. So now I can either encode the red ones into the green ones and then into the white one, or I can directly include the red one into the big one. Okay, so we have the O's. I don't want to bother with too many indices, so just write it schematically like this. This sits in U1. It's in U2, and possibly more. Now, B sits inside B.
Do they have to be finite or no?
Yes. Yes.
The disjoint uni, do you mean that they must be disjoint?
Yes. They must be disjoint. I really mean disjoint.
Is this map always injective?
Which map?
The inclusion map.
This one here, F?
Yes.
No.
QFT, right?
I mean, in certain examples it will be, but in the definition here, it's not. I will, let me give you an example later on. I mean, it doesn't often it doesn't even make sense to say it is injective. Okay, wait for an example.
But AQFT will be an example, right?
If you go to that, and like, that's one of the sort of classical axioms in AQFT, but it's also often recently it's been weakened, that axiom.
So there are comparison papers, for instance, like on the BB quantization, that's been done in both situations by Kaschner-Reitzner and Owen William. There are comparisons. But note, for instance, that I'm never requiring A of U to be an algebra. It's really just an object in S. So, I mean, there's something obviously different about the definitions. And again, like, wait a couple minutes and then you will see an example that motivates that there is a connection.
In QFT, it's sort of maximally not injective.
Yes, that's the example. So I for such an inclusion, then I have, well, inclusion maps. This. And then into A of V, or I could have gone straight here, and this should commute. So if we're in vector spaces, the example that we just said, this really commutes on the nose. But in general, we're working in an infinity category setting, so I didn't write what this is. But for instance, in the BV setting, we really want this to be something like chains. And then this should be an infinity one category, which is the metric monoidal. And then we can just ask for this to commute in a coherent way. So here now, I mean, without going more into details of infinity one categories, I can't really tell you much about this, but let me just say this is a useful way of organizing this phenomenon. All right. So 2 remarks. So this makes sense. Or something smaller than all opens. Any partially ordered set of opens. And the language, again, I want to use the higher category stuff just as a language at this point of Avrads and infinity one cats packages this nicely. Let me do the example first. I still have a pre up at the board, so there should be something non-pre. So let's see how this here fits into the framework, algebras. Example 1, let's take X to be R. Let's start with A, an algebra. So I can define give these names A, curly A. A on opens, which are intervals, as follows. So any interval I send to A. This is a straight A now. Now, if I have disjoint union of intervals sitting inside a larger one, I1 disjoint union I2 sitting inside I3, my larger one, I have to give you a map from A of I1 tensor A of I2 to A of I3. Well, this by definition is A. This by definition is A. And this by definition is A. So I have to give you a map like this. And I will use my algebra map. So Ryan, here's an example where it's not at all injective. So if you now have like several copies of the interval of the intervals, you just have several copies of the algebra, and then you use multiplication. And this funny condition that I wrote down here, this coherence condition, translates to associativity. So there's one thing I have not told you about yet. There's also an empty set. Empty set I will not send to A. I will send the empty set to the ground field. So over some field K. And there's a map like this, and that will be the unit. And the other example, we want a Morita category with 1 bimodules. X equals R, but now I choose a point. Okay, let's just take 0. And now I take a bimodule. For AB. I draw my point. And now what I do is, to any interval on this side, I assign A. To any interval on the other side, I assign B. And to any interval containing the point, I assign M. So for instance, you could take the disjoint union of those 3 guys and send it to this large interval. That's again a green interval. It has a point. So it goes to this. So I have to give you a map like this, and that's the bimodule action. So again, I get something defined on this int. Call this curly A on int. But there's one extra piece missing, namely I again have empty sets. So I can include my empty set, include this into a green interval. And this here is assigned M. To the empty sets, I mean, there will be a more general property, but empty sets I always want to assign K. So I have to give you a map like this. So I have to choose a point. Okay, so I need, in addition to have some chosen points, this is not. So these are both pre-factorization algebras. We'll talk. Some comments I can make. Oh yeah, one more comment maybe. One more example. So if we take R2, then I have to assign things that look like this. And so, I mean, some of you might have seen this. If not, don't worry about it. But structures like this are called E2 structures. This is the operate of little Q disks. And there's a fact that any E2 algebra A gives me a factorization algebra on R2. And so what I want you to see is in particular, that means I have, if I denote, if I say any desk goes to A, this goes to A, then I get an operation like this. Now I can start moving my disks around. And in particular, at some point, they might have rotated, switched order, and then I get the opposite thing. So if we're in vector spaces, S is vector spaces, then a structure like this will actually be a commutative structure. If we're in categories, a structure like this will be a braided monoidal structure. And I mean, there are vast generalizations of this, but maybe this is a good place to stop here. After the break, well, after Ryan's talk, we'll continue talking on how to actually get a Morita category.